let me introduce Dorothy. So like I said, she's on the core systems team at Twitter. She went to UBC and she's either been in or adjacent to the Scala community and has spoken at Scala conferences, including the Type Level Summit in 2018. She's originally from Toronto, and after a stint in San Francisco, she's now in Vancouver. And her hobbies include dancing and eating chocolate. I'll leave the rest to her, though. Shannon is on the call. Did you want to say anything before we got the talk started, or do you want to save that for after?
We could say, well, thank you everyone for joining. This is the first time I've ever thrown a virtual meetup, so bear with me, and I do apologize in advance. But yeah, I'm just thrilled to have everyone on board, and I'm excited for today.
Okay. All right, with that, let's just dive right in. Dorothy, it's all yours.
Thank you for that lovely introduction. So I'm very excited to be here today. Thank you for inviting me. My name is Dorothy Ordogh, as Sean had said. I'm a software engineer on the Core Systems Libraries team at Twitter. My team develops the core libraries that most services at Twitter use. Today, I will be talking about how we use core principle of functional programming, specifically function composition, to create and maintain Finagle's extensible and robust RPC system. Additionally, to describing how we've improved our lives as Finagle's owners by really leaning into function composition when configuring clients and servers. In today's presentation, I will first do a quick overview of function composition. Next, I'll briefly describe how our services in Finagle are defined, how we use to configure clients and servers that our customers use, and then how we developed a way to more simply compose protocol agnostic modules to hide complex logic from our customers and modularize concerns to improve client and server configuration. It's a lot of words. Let's dive in. So as someone who's pretty forgetful, I can appreciate that unless you encounter some of the following words regularly, they're easy to forget. And also I'd like to have everyone be on the same page. So let's go through some terminology. Protocol agnostic means that the thing being referred to is designed to be compatible with different protocols. RPC is remote procedure call. Robust means healthy and strong. Extensible means capable of being extended. And module is an independent, operable unit of a larger system. All right, let's move on to function composition. I'm sure everyone knows the concept of function composition, but it's worth a review. The very simplest definition of function composition is combining functions by passing the result of one function as input to the next to create more complex functions. H of x equals g of f of x. This is a very simple example. This can be done in most programming languages, irrespective of whether it is a functional language or not. You should be able to call a method inside the call of another method. Here, I've defined a few function literals as examples. The first is a function that multiplies a given number by 10. The second adds 100 to a given number. The third is a function with a terrible name, but it composes the two functions into one. When I call math is fun with 1, it will be multiplied by 10, and then 100 will be added to the result. Now, giving us 110. Now, a basic tenet of functional programming is that functions can be treated like variables, and they can be passed as arguments to other functions. This allows for an even broader type of function composition. in Scala, a functional language where functions can be treated as variables, we can use Scala's built-in and then function to compose the two functions I showed you earlier, just like we did before. As you can see, the ordering is different, but it's executed in the same order as before, and we get the same result with the same input, that is 110. So let's now talk about a Finagle service. A Finagle service is actually just a simple function that takes a request type as a parameter and returns the future of a response type. Both the client and server use service in their implementations. An example of this would be this. This is a protocol-specific example of how we use a protocol-agnostic concept like service. This is specific to the HTTP protocol. Here you can see that we define the business logic in the services apply method. Here on a request, the service will return a 200 response. Now let's tie this into an example using our multiply and add functions. Here I created a trait called number service, where the request and response types are integers. However, this could easily be a service with rec and rep as the request and response types, just as I've shown you in the previous slides. Finagle implements a lot of complex RPC logic that is protocol agnostic in terms of a service. And remember, a service is a function. The interface for service is a little thicker than what you see here. There are more methods, but the core concept is the same. It has an apply method. Then each piece of the RPC logic is encapsulated into its own function / module in order to make it easier to reason about and to test independently, just like add 100 and multiply by 10 are here. Components like timeouts, retries, backoffs, load balancers, admission controllers, etc., are all implemented in terms of a service and as separate modules like these, but they're quite a bit more complicated. The modules are then stitched together via function composition to create complex behavior. In this example, you could imagine that the badly named math is fun function is actually the client or server. And again, when we compute math is fun with 1 as the argument, we get 110 as the result. So this is all great, but we rarely find that we can hard code values into our modules like I have in multiply by 10 and add 100. So let's change things a little so we can configure the value we want to add and multiply. In this example, each module has its own state. That is the number that we are configuring. But how do we define math is fun with all of the configurations? With only 2 modules, it's pretty easy. I have the multiply with the configuration of 10 and add with the configuration of 100. But as soon as you have 15 to 20 modules, this becomes far more complex. In Finagle, despite the fact that we try to provide a reasonable default that works for most services, we need to allow the client and server creators to configure their modules to their specific needs. So let's look at the client and server and how they were defined in the early days of Finagle. So first, to solidify this example, I want to define protocol agnostic modules that implement some component of RPC logic. Here we have the ConnectionFull and the request timeout modules. And they both require some kind of configuration. In the case of the ConnectionFull, it's the ConnectionFull size And in the case of the request timeout, it's the timeout duration. Now, back in the day, terribly sorry. Back in the day, you could just define everything that you needed in the default client. Terribly sorry, my slides are behaving poorly. Sorry about that. Do you see this?
Yeah, we got the speaker view.
Darn. Sorry, folks. Just 1 second. Okay. Sorry, everyone.
It's all good. Don't worry about it.
All right. Let's get back to things. Sorry, I'm just reading some of the chat. Thank you for being so nice. All right, back to the top. I'll start with, now back in the day, the client and server were defined as a function with all of the configurations passed in as parameters to the function, like you see here with the default client. All of the components had a default configuration, but to allow for service owners to tune their services, just like I said in the last slide, they could customize their configuration by calling default client with their own configs. And you can see here that we would first create the modules with their configurations that we passed in, and then we'd compose them together using and then. As more functionality was added and more components were added to Finagle to increase resilience and to improve recovery, these functions became massive. They were changing a lot, which made them very hard to manage and made them even less extensible. So the system was redesigned. Using a collection of modules and configuration params that materialize on client or server creation, we could solve this ever-changing constructor issue. Let's take a look. First, there's the Finagle stack, a key component used to store modules or functions you want to compose. It is essentially an immutable ordered set of modules. You can see here that it's implemented similarly to a linked list. Each module is defined as either a leaf or a node, and the node is pointing to the next module in the stack. Then, stack params are the key to configuring the modules in the stack. Params are an immutable set of typed parameters. They are defined as objects, and they live where the modules are defined. Each param has a default value, and under the hood, the collection of params is implemented as a map. Now let's see how they work together. All right, to exemplify how the stack and params work together, we will implement a simple version of the request timeout module. This module will cancel a request if the configure timeout duration has elapsed. As you can see, we define a class within the module that is the stack param configuration of this module. In this case, timeout param. We pass in the timeout duration. The param has a companion object where we define the default value for the configuration and provide a way to easily retrieve the value from the stack. Next, we define a module that will be added to the stack. In this module, we define the most important piece of the stack module, the make method. It is what is called when it is time to materialize all of the modules in the stack. In this method, you see that we first extract from the stack the param that we need to configure in the module. Then we create the request timeout module and compose it with the next element in the stack with and then. This is how stack modules and stack params work together. Now, let's add to this example before we show how we materialize it and how it works with a client or server. Here we define the ConnectionFull module. This module defines the logic for keeping a configured number of connections open through the life of a server or client. It's just another module that contains more RPC logic. As you can see, the module has a make method defined, and it will do the exact same thing that we just saw. It will extract the parameter from the stack, and it will create the ConnectionFull object and compose it with the next element in the stack. Okay, so let's now define the client and/or server. Ta-da! Here we have the client object, which could just as easily be the server object. In the object, we declare a stack builder to help us build up the stack. Then we add the request timeout and ConnectionFull modules to the stack by calling the stack builder's push method. Finally, we get the final stack of all of the modules we want for this client and/or server. This is an immutable stack, and we materialize it when initializing the client or server. Speaking of which, when the client or server is being initialized, we call make according to the order of the modules in the stack. Now, remember when I mentioned that how the stack is an ordered set and how each module's make method will compose with the next element in the stack? Yeah, well, that is what's happening during initialization, right before connections are being made. The modules are composed together just as functions are, one calling the next. Now let's take a look at how we configure clients and servers with this new design. Here we have an HTTP protocol specific client. The protocol specific logic lives in its own module, and the http.client is an interface for the protocol agnostic client combined with the HTTP protocol module. It should be noted that the client is immutable and can be copied along with all of its modules and params. In our client and also our servers, we define a .with API to easily configure clients and servers. The .with methods are decorators on the immutable collection of params. With this API, and in the case of with ConnectionFull, we are adding the respective param to the stack. That is the ConnectionFull param with the pool size configuration. Again, we use the .with API to configure the timeout param with our desired timeout duration. And then we call new service with the IP address and port number. This is when everything is materialized just before the connection is made. So I just want to re-emphasize that the base client is protocol agnostic, and we can create protocol specific interfaces by combining the same base client and/or server with protocol specific modules. Some additional examples are our thrift client, our memcached client, and our MySQL client. And to finish up, I'd like to go over some of the pros and cons of this design. Let's start with the positives. This design is modularized and protocol agnostic. We don't have to worry about mixing concerns, which can make each individual module a lot easier to reason about. The params are defined with the module, so you don't have to guess where it's coming from. And again, all of the concerns for a single module live together. Because everything is modularized, it becomes much easier to test the logic. This is extremely important in a complex and mission-critical system like this. The client and/or server constructor remains the same even when we need to add or remove functionality. This is because the configuration is all done with the params and/or the .will API. And finally, it is more maintainable because of all of the points I just mentioned. Now for some of the not so positives. The params are type checked, but they could be misleading because they're checked at the stack level. When you define a param at the module level and use it in the module, it's type checked, which is great. But it is possible to add params to the stack at any point, which can also be great because it's flexible. But imagine adding a param to the stack and just believing that the module will work. But if you haven't added the module to the stack, then it just fails silently. And you might even expect an error to be thrown, but that doesn't happen either. So it can be a little confusing. Next, the ordering is very important. Because every module is complex and keeps an internal state for performance purposes, for which we're also providing configurations, ordering is very, very important. There are some modules that must execute before other modules. An example of this would be the add and multiply example. We needed to multiply first to get the expected result. We also need to multiply first because of math. And finally, how all of the modules work together can be very hard to reason about. The ordering and what functionality encapsulates another can be somewhat hard to understand, especially when there are many modules with a lot of complex behavior. But for us, the cons are totally worth it, especially since most people on the team won't need to touch the ordering of the modules in the client or server. And if they do, they have very nice stack experts to help them. The other positive of this is that because we're library owners, customers at Twitter don't need to worry about this either, which is great. They shouldn't have to worry about this. It should just work. All right, and that is how we use function composition to create a robust and extensible RPC system. Please note, all of this is open sourced, so you can take a look on GitHub yourself, which is really cool. And feel free to ask us questions or raise issues. Thank you. Now I'm happy to answer any questions.
Thanks, Dorothy. People should be able to unmute themselves if they have any questions. So let's just open the floor for a bit, and then we'll move on to the next part.
So I see a question. Sorry, did you have something to say?
No, I was just gonna probably say the same thing as you, that you can use the chat as well.
Yeah, I see a question in the chat about what thrift is. Protocol buffers is very vague, but thrift is another type of protocol. It's similar to like you said, protobufs, Google's protobufs, just an older version, and it's by Apache. And then there's another question. What RPC system are Twitter services using to communicate internally? It varies. We have an internal protocol that we actually also created called MUX, so that most legacy services use Thrift MUX, so combination of MUX and Thrift, but many services also use HTTP. It depends on their specific needs, which is why we try to build, as protocol agnostic of a system as we can, so that we can serve all of our customers. No problem.
Okay. If there are no other questions, oh, we got one more question.
Is the team at Twitter working on integrating HTTP2 into Finagle? The answer is yes. We do have a HTTP2 module in Finagle, and you can see that on our GitHub. The second question, can it automatically fall back to memory sharing protocols like Apache Arrow if allowed? We haven't explored this as far as I know. So I'm gonna say for now, no. I would say no. We use non-memory sharing protocols. Next question, how do exceptions flow? Sorry, trying to parse the question. Okay, and so how do the exceptions flow through the function composition chains? This is a great question and is very complex, but essentially the same way. It's up the execution order, and then passes it on to the next and to the next and to the next and to the next. And we also define things like response classifiers so that it, if you receive an exception that, I don't know, maybe is ignorable, you can set it to ignorable and then you don't have to worry that your service is going to fail on it. And that's also a module that we mix in through function composition. These questions are great. Thank you. So next question, I'm assuming when you say future, you mean Twitter's future. Do you have any instrumentation / tracing compatibility to see exceptions, traces as in asynchronous scenarios? We 100% have tracing, and you're right, that is Twitter's future. But yeah, we absolutely have tracing. We have stats collectors, and which is also where these exceptions get reported. We also have like a form of Zipkin that traces each call along its route. I think Zipkin is old. We now use a different terminology for it. It's not coming to me. I'll think of it. Yeah, I hope that answers the question. I'm not sure what Cat's effect and ZIO is. I hope you don't hate me. Sorry.
That's all right. I was just asking because they're similar sort of effect systems. So, when you do things asynchronously with sort of the Scala standard feature, you sort of just get this weird, you sort of get the internals of future in your exception traces, and it's sort of like harder to debug. So I was just wondering if sort of Twitter features had something similar, because what they do is they like sort of augment the code and then they sort of give you sort of where it failed and where it was supposed to continue. So it's more useful than the async internals of the effect.
Got it. So our Twitter features have all of this built into them, which is why we opted to create Twitter features rather than use Scala's features. Also, at the time, Scala didn't have features when Twitter features were first created.
Cool, thank you.
Yeah, it's all built in.
Yeah, I just wanted to mention that the Scala team at Whiteband is actually working on improving stack traces with asynchronous exceptions that happen in the future. So I'm not sure when that's going to be released, but I used to work at Whiteband. I just left a few months ago, but I know it's in the works.
That's awesome.
Well, if there's no other questions today, feel free to reach out. Our email addresses we pinged it over into the chat. Connect with us on LinkedIn. We're always available on Twitter too as well. Find us. But again, thank you for taking the time to join us. And Dorothy, thank you again for giving a overview, and that presentation was wonderful. And have a great night, everyone. I'm on the East Coast. I don't know if people are on the West Coast during the day, but have a great night and have a great week, and feel free to reach out if you have any questions. Thank you.
Yeah.
Bye.
Thank you very much, everybody.
Thank you.
Thank you, Dorothy, for presenting. And thank you for attending. I'm really sorry that we haven't been as active with our meetings and our meetups. Hope to get that back on track, especially with the great folks at Twitter. Yeah, if you guys have any talks or any ideas for talks, please feel free to hit up either Sean or me, join the Slack, be a part of the community. If you're looking for jobs, there's plenty of jobs out there, which is really great. I'm so happy to see that there's so many more Scala opportunities in Toronto. And yeah, I just wanted to thank you all for being here, and till we meet again. Cheers, everyone.
Thank you.